speak today. Yes, all
Yes.
yours.
Okay, thank you. Thank you very much, Shonan, for the introduction. So let me share my screen. Can you see my screen now?
Yeah, perfect. It's a full screen mode. Thank
Okay,
you.
so hello everyone. So it's very honored to be back to the UNIFI seminar series and represent our UNIFI consortium modeling and simulation team to introduce this major accomplishment we have made in the past several years. It's basically, we will introduce this WECC-approved standard library grid-forming inverter models, REGFM A1 and REGFM B1. First, some little background information. So why these standard library grid-forming inverter models are important? So we know that there are standard library models, user-defined positive sequence phasor domain models, and EMT models. All these models are very important. They have different application scenarios. Here, this presentation will not discuss all those how to use these models, but I think some organization like NERC, they already have a lot of guidelines on that. But this presentation will mainly talk about the standard library models because we think the standard library models are very important for the interconnection-wide base case creation and many other planning studies, especially when people doing the long-term planning studies when this grid-forming inverter user-defined or manufacturers black box models are not available for those long-term planning studies. And also, if you read the most recent FERC Order 901, you also see the importance of the of the standard library models. You can see the code here. It's the FERC Order 901 requires the use of approved industry generic library IBR models that accurately reflect the behavior of IBRs during steady state, short circuit, and dynamic conditions when developing planning, operations, and interconnection-wide models. It just emphasizes the importance of those industry-approved generic library models. And also, I also learned a lot from reading this FERC Order 901. It has a lot of discussions regarding user-defined model or industry-approved generic models. It's pretty interesting. So if you are interested in this practical issues in this IBR modeling world, I would recommend you to read this order. And also very important thing is that we know the importance of standard library IBR models, but before the UNIFI consortium, before we initiated this work, there were no standard library grid-forming inverter models in today's commercial transient stability simulation tools. We know that maybe in the US, PSSE, PowerWord, PSF, TSATs are mostly widely used, right, for those transmission planning tools. But there were no grid-forming inverter models in those tools. So we know the importance of grid-forming inverters, right? But the planners need very good models to do their planning studies to understand what benefits the grid-forming inverters can bring to the system. That's why we think this work is important. That's why our UNIFI consortium, we developed those accurate industry-approved standard library grid-forming inverter models for transmission planners to better understand grid-forming technology. And hopefully that can help advance the grid-forming technology toward wide adoption. So this is a little bit of background information. And this slide just shows the WECC announcement of those two models. I think the WECC, we closely work with the WECC modeling and validation subcommittee, and you can see they approved the two models. One, the first model is called REGFM A1, approved in September 2023, last year, and the most recent one is REGFM B1, approved by WECC in May, actually, this year. So we believe those two models represent two mainstream grid-forming controls used in industry. It's mainly droop control and virtual synchronous machine control. And also, as mentioned, because there were no standard library grid-forming inverter models in those commercial tools, these two models have become the first WECC-approved grid-forming inverter models and have been integrated into those the world-leading commercial simulation tools, I would say, because we know that PSSE, PSF, PowerWord, and TSAT are really widely used around the world, not only in the US. And some people ask me which version can they find these tools, and then so you can see that you can find those models in these versions. So this is just the announcement of this accomplishment. And then here is a little bit details about how those model specifications were developed, how those models were developed. So this is really a collaboration between research institutions, inverter manufacturers, software vendors, and system planners. So in the past several years, we worked very closely on developing those public standard library grid forming inverter models. For example, for the REGFM A1 model, that was the first model, we leveraged some previous DOE work on microgrids, but also we got some valuable comments from SMA for this model. And for our GFM B1 model, we got a strong support from GE for developing this virtual synchronous machine model. And then when we developed this initial model specifications, we submitted to the WECC modeling and validation subcommittee. There were a lot of system planners and also software vendors there. So we discussed these model specifications, understand them, and then maybe add some more, address some comments from software vendors from implementation perspective. And finally, after multiple rounds of revisions, updates, we reach a consensus at WECC. So finally, we get a WECC, the members approved to the use of these standard library models. So this is just how these models were developed. I would say that's a really strong collaboration between research institutions, inverter manufacturers, and software vendors, and system planners. You can see research institution, we have PNL and EPRI. Manufacturers, we have SMA, GE, SGRE, and also recently Tesla joined us. Software vendors, we have those 4 major commercial trans-specific simulation tools, and also WECC members. So finally, we reach a consensus around WECC members and get them approved and released in the commercial tools. So that's really a collaboration. And here I also like to acknowledge all the each individual contributors to these models. If you find the model specification of those 2 models, you will find their names in the document. We really appreciate all their support, from multiple organizations. Thank you. So and then we'll talk a little bit. Another thing is that when we develop these models, we also reference some industry specifications that can provide guidelines, also high-level guidelines for us to develop those models. We of course reference our own UNIFI grid forming specification, and also reference the NERC grid forming functional specification. Especially for the NERC functional specification, they define several 3 loss of last synchronous generator case to verify the grid forming functionality. So of course, REGFM A1 and B1 can pass all the 3 test cases because they represent grid forming technology. Okay, so after those kind of high-level introduction, now we're diving into some details of this the first model, REGFM A1 model. Here shows the timeline, how this model was finally approved. Actually, it took like more than 2 or even 3 years to get the first model approved, because that was really, we need to spend a lot of time to help industry understand this technology. So actually, before we start this work, actually at PNL, we have done a lot of microgrid work, actually which use a lot of grid forming inverters. So based on our previous work, we submitted the first grid forming inverter model specification to WECC and got their approval in December 2021. And then after that, NERC sent this model specification to several manufacturers, grid forming manufacturers. And SMA actually is the first manufacturer who provided comments to this model. We appreciate their support. And they said the model looks quite good to represent the key elements. And also they provided some detailed suggestions. And when we received their suggestions, we carefully review them. And we think both their suggestions are very reasonable, so that we include their suggestions in the updated version of the model specification. And finally, we work with all the software vendors to implement and benchmark this model, and then finally get approvals in this model in September 2023. So you can see this process took several years, because that really took a lot of time for us to explain this to industry and help them understand this technology for both software vendors and system planners. And then we understand the applicability and the limitation, and finally get the model approved and released. And then these slides just show the core control blocks of this model. First, we think this REGFM-A1 is a grid forming inverter, so it is represented as a voltage phasor behind impedance, right? Because it is grid forming, so it is a voltage phasor behind impedance. And also it represents a droop control. Because it represents droop control, we have this simple power versus frequency droop control, and also reactive power versus voltage control, two droop control. And also we have, because your grid forming inverter is not an infinite bus, it has its own limitations, power limitations, current limitations. With this model, we also have some pretty good steady state active power and a reactive power limiting control. You can see this reactive power limiting control was recommended by SMA. And also we have a steady state P and Q limiting. Also we have the transient current limiting function, which is approximately to the equivalent to a virtual impedance to represent the short circuit fault current limiting. And then, this is just the overall overview of all the control blocks for this REGFM-A1 model. I do not have time to explain all the details, but I assume that this is the first version, and I think many people probably know droop control well, so I don't need to explain all the detail in this presentation. But here I just like to talk about a little bit the model validation and what's the benefits that grid forming inverter can bring to the system. So when we developed this first model, the droop-based RGFM A1 model, we sent this model to a transmission planner in BPA area. So Dimitri, he used this model, he ran some PSIF simulation to study the micro WECC system. In the micro WECC system, it's very small system to represent the micro WECC system. And he just studied, when we have high penetration of IBRs, if these IBRs have some headroom, if they are grid forming or grid falling, how they will impact the system frequency response. And then he was shocked by this green line, which was using the REGFM-A1 model with 73% penetration of grid forming in the micro WECC system, and with some headroom. And then he saw the frequency just like this. It's just primary frequency response was significantly improved, and he never saw this kind of stable frequency response in the past. After loss of generation event, he told me he was kind of shocked by this model, and he didn't understand what's going on there. And then I tried to explain to him, because the grid forming inverter is just a voltage phasor behind impedance, right? It responds to all the load change autonomously, and because it follow the droop control, it just the frequency just change from one steady state to another steady state, and just very stable. And he seems to convinced understand the results, but it's still simulation. And also recently, we find some amazing work done by SMA team. They published a paper with some hardware testing results with this grid forming inverter. You can see that what they did is that they have the single inverter and the synchronous machine working in parallel, and then did a load change to test the system frequency response. And they implement the inverter control with different controls, including grid forming, droop control, grid forming, inertia control, and also grid following control. So if you just look at this blue line, you can see when they implement the grid forming droop control, how stable the frequency is, right? How this kind of grid forming control can improve the frequency response of this small system. And the results just look very similar to the simulation results at the left side. I think this is just the main characteristic of grid forming droop control. They can really stabilize your frequency as you have enough headroom. And I think they really did a fantastic job on demonstrating the benefit of this grid forming control during normal operation. And another important thing is also currently a very active research area is the fault rise through control of grid forming inverters, and when during the severe fault, how the grid forming inverter responds to the fault. And for this REGFM-A1 model, we have a very simple transient current limiting function, which is approximately equivalent to a virtual impedance. That means during a short circuit fault, we are inserting a very large virtual reactance to limit the current. So this approach is pretty simple and is widely reported in literature. So it works pretty well for some short typical faults like that are quickly cleared by the protection devices, like a 6-cycle fault, or 0.1 cycle fault. During the fault, we can see the inverter stays at its maximum current limiting, and then after the fault is cleared, it can quickly go back to stable and doesn't have any issues. But also we have already done some theoretical analysis, have some papers published here. When we implement this kind of virtual impedance as a fault current limiting strategy, it has a kind of critical clearing time. That means that when the fault lasts too long, for example, if I add a 1-second short circuit fault, we will see that after fault is cleared, somehow this REGFM A1 model lose synchronism to the grid after long-term fault. So this is something we want to be people to be aware of, because at that time, back to several years ago, 2 years ago, we don't have very good current limiting control at this stage, and also this is still very active research. We have those several papers to explain that. Actually, this is very similar to a synchronous machine. Assuming you have a synchronous machine put here, if you add a 1-second fault, that synchronous machine will lost synchronism to the grid either, right? So this is just one I would say the limitation for this model, and also still very active research is going on in this area. And here I like to summarize the applicability and the limitation of this model. You can see here, I think this model is quite good to study the many typical events like frequency response, islanding and islanding operation, and trip of generators and trip of lines, and typical faults with normal clearing time and even overload testing. But we don't recommend to use this model to study some long-term severe faults like those delayed clearing faults. This is because this model is a generic model. It does not include all the details from manufacturers. We appreciate the manufacturers provided information as much as they can to develop these models, but there are some proprietary technologies there that not reflected in this model. So we will see that if you want to study those long-term severe faults, we really recommend you to reach out to manufacturers, and we believe they have better those current limiting fault rise-through control algorithm in their black box models. And when we approve this model, we know the applicability and the limitation of this model, and then we are also working on improving and updating this model for the next version, for example, REGFM A2. And then I will introduce the newest model, the second model approved by WECC recently, is REGFM B1 model, which represent a virtual synchronous machine. And here shows the timeline for this model approve process. Because of the work we have done in the first model, so now the WECC industry and also the software vendors have a better understanding of this basic concept of grid forming. So which actually helped the expedite approval of the second model. So you can see for the second model, it just took 1 year to get approved. And this second model was mainly supported by GE, and also we work with EPRI on the UNIFI consortium to develop this model, and then finally approved and released in the commercial tools in May 2024, actually just this year. This model, this slide just shows the main control blocks of this REGFM B1 model. You can see first is still a voltage phasor behind the impedance, because this is grid forming. And then it has a virtual synchronous machine inertia control block, right? Because this is a virtual synchronous machine, you can see some inertia time constant damping in the control blocks. And also it has a voltage control block, which is very similar to a synchronous machine exciter control or AVR control. And also one thing I like to highlight is that this model being different from a simple synchronous machine swing equation, this model has a phasor lock loop involved in the control blocks. Some people might get confused why the phasor lock loop is used by grid forming inverters, because people think maybe only grid falling inverters use PL, right? But here I like to emphasize that the use of this PL is fundamentally different from how a grid following inverter uses PL. So the use of PL here is meaning to address that kind of phasor loss of synchronism as I mentioned previously. So this PL can be considered as not existent during normal operation. So you can see that because here we have a delta omega PLL and a delta PLL. And the integration of delta omega PL is delta PL, right? So here you can see a minus sign here and the positive sign here. So actually they cancel out with each other during normal operation. So as long as these saturation limits, delta IT max and delta IT min are not reached, they canceled out with each other. So they can be considered as not existent. But during some severe faults, when this phase angle reaches the saturation limits, this PL will be activated somehow to maintain your phase angle stay synchronism. So I will explain more in the next slide. And as I mentioned, this model really received strong support from GE, and we appreciate their support. And I saw some GE folks here. GE provided an advanced current limiting solution, including the steady state, active, and reactive current limiting controls. So we can see that the active current limiting control is how do they do the active current limiting control is that keeping in mind that our grid forming inverter is a voltage phasor. So if we want to limit the output current, we regulate the voltage magnitude and the phase angle of this voltage phasor. So for this active current limiting, what they do is that we limit the active current by regulating the phase angle of this internal angle. So you can see we have the current loop here. Once the current exceeds ID max, and this will be activated to reduce these saturation limits. By reducing these saturation limits, actually you can limit your output active current. So this is how they do the active current limiting control. And also the second thing, right, because you limit your active current, you also want to limit your reactive current. And also, again, keep in mind that the voltage grid forming inverter is a voltage phasor. And then by limiting the output current, we need to limit the angle and the magnitude. For the reactive current, what we do here is that we limit the internal voltage magnitude based on this simple algorithm. So once my IQ exceeds the limits, so we have this equation, an algorithm activated to quickly reduce my internal voltage magnitude. By reducing my internal voltage magnitude, and we can limit the reactive current output. So by reducing your internal voltage magnitude, you can limit the reactive current. So you can see we limit the active current by regulating the angle and limit the reactive current by regulating the internal voltage magnitude. And also we can use some PQ priority algorithm to determine your ID max and IQ max, right? Because you want to know how much active current you want to limit and how much reactive current you want to limit. So that's why we have a PQ priority algorithm to determine that. So this is somehow similar to a grid following inverter because the WECC grid forming IBR model also have the PQ priority, but the current limiting approaches are different. But also it can use but even for this grid forming, we can also use this PQ priority algorithm. And also this model has also has a transient current limiting function, which is very similar to what we have done in our GFM A1. It aims to represent a kind of virtual impedance control for your initial stage of current limiting. Because at the beginning of a fault, this model actually can have two-stage current limiting. The initial stage is more like something like a virtual impedance, and the second stage will start to change your voltage magnitude and phase angle to rise through the long-term fault. Yeah, I know this kind of explanation is maybe complicated. So here I like to use one example to show how this fault rise through control works, because this is something that I know many researchers, if you are doing the grid forming control, you care about the fault rise through and current limiting. I know that. So here we will show an example to show how this control works. So you can see we have a single grid forming inverter connect to an infinite bus system. And again, if we apply a long-term fault, you can see, look at this PSCAD simulation. At the beginning of fault, we have a little bit overcurrent, but this was clamped by our PWM PWM level current clipping algorithm, maybe at 1.5 per unit. And then our steady state current limiting control quickly activated to limit the steady state current. You can see here our reactive current is quickly limited by quickly reducing our internal voltage magnitude using this Emax and Emin controller using this algorithm. So this algorithm is activated very quickly activated to reduce the reactive current. So you can see the reactive current is limited at their IQ max. And then for the active current, is also activated to limit the active current. And then during the fault, because your phase angle is going to lose synchronism to the grid, because we have saturation limits here, delta IT max and delta IT min, it somehow clamps the phase angle difference across that inductance. By clamp the phase angle difference across that inductance, actually, we somehow clamp the limit the internal phase angle delta VSM. So by limiting the clamp the internal phase angle delta VSM, that phase angle does not lose synchronism to the grid, so that during the fault, its phase angle is somehow clamped. It will not lose synchronism. And after the fault is cleared, it can quickly quit the current limiting mode and go back to its previous operation mode. So this is just how this process works. So you can see we have a stage one at the PWM layer to clip the current at the very beginning, and then our stage two active and reactive current limiting control actually provided by GE can rise through this long-term fault. And then after the fault is cleared, it can quickly go back to the previous mode. And then here, because the purpose here is not to develop EMT model, although every time when we develop these models, we develop an EMT model to verify its performance. And then, but the goal is to develop positive sequence model to get them in commercial transient stability simulation tools, so that transmission planners can really evaluate in their practical large scale system. So here, first I use the EMT model as an example to explain how it works. And here, I like to show some comparison results between the PSSE model and the EMT positive sequence model and the EMT model. Here, we did a very rigorous comparison because we really want to know if those positive sequence models are accurate enough to study the system transient stability. So we did a very rigorous comparison. So we made sure the PSGAD model has all the details, has switching for the IGBT, right? Has all the PWM controls. But for the positive sequence model, we have to ignore those PWM controls, but many models the outer control loops. And then we compared 18 critical variables because we want to do a very serious comparison. We just not compare P and Q, we compared all the 18 critical variables. So here just show one example for that 1 second fault, just for the fault case I showed before. You can see we compared PSSE and the PSGAD for 18 variables, including your PQ, voltage, frequency, your internal voltage, ID, IQ, angle. They matched pretty well. So they just show that PSSE, this kind of positive sequence tool, is still pretty good to study, at least for the behavior of grid forming inverters. And we just show one example here. Actually, we did a tons of simulation comparison for many different cases based on that single inverter infinite bus system. They can all achieve this level of accuracy even with low short circuit ratio. Just to explain why we can, even for the phasor model, it can give such level of accuracy. So because your grid forming inverter is voltage phasor behind the impedance, it's actually very similar to a synchronous machine in many ways. For a synchronous machine, right, people know that this PSSE model is pretty good to study their transient stability. You probably don't need an EMT model to study the transient stability of synchronous machine. I think most people agree with me that right? And we know you have to use EMT model to study the subsynchronous oscillation caused by synchronous machine, but for transient stability, probably you don't need that. That's why for grid forming inverter models, because it's voltage phasor behind the impedance, it's kind of similar to synchronous machines in many ways. So that's why we think so far this kind of positive sequence model can still capture the behavior of grid forming inverters very well. This is different from grid following. Grid following, I believe, positive sequence model has their big limitations. And here I'd like to talk about a little bit about some real-world events. Because on the UNIFI consortium, we also work with NREL team. NREL, they work very closely with Hawaii Island, with HICO. So I think back to last year, in Hawaii Island area, there were two grid forming inverters in their island. They saw some interesting 1 Hz oscillation, as shown in the left side. This is between two grid forming inverters. And then the PI Jean Tan from NREL, she asked me, can you use your generic grid forming inverter models to reproduce this kind of, to analyze this 1 Hz oscillation? And then we use our industry approved generic models to set up simple case and to tune some parameters, and then we are able to reproduce this kind of 1 Hz oscillation. Note that even this is not very high frequency oscillation. This is low frequency oscillation, right? It's 1 Hz. So theoretically, I think we should be able to reproduce that using phasor model. And you can see that by tuning those parameters, we are able to represent that kind of 1 Hz oscillation. So this is kind of interesting. But we are further working with them to find the root cause for this oscillation. We did some initial simulation we can reproduce this 1 Hz oscillation, but it doesn't mean that we find the actual root cause for this oscillation, right? So this is still ongoing, and I think Xiaonan is leading this task. Actually, we are working with Xiaonan and NREL team to further analyze this kind of 1 Hz oscillation. And another interesting project I'd like to mention that is also really related to this RGFM B1 model is a real-world demonstration project. Other than UNIFI Consortium, we have another real-world demonstration project on the 380 megawatt wind, solar, and battery storage combined power plant. This plant is actually very unique in the US because it's called Wheat Ridge Renewable Energy Facility, because it's North America's first energy center to combine wind, solar, and battery storage in one location. You can see that we have 300 megawatt of wind, 50 megawatt of solar, and 30 megawatt of energy storage systems. So we got this award from DOE Solar Office maybe 2 years ago. And this project was led by our host utility, Portland General Electric, and also GE as a major manufacturer are in this team. And also we have system planners, BPA, system operators, BPA, and also plant owner next year, and also University of Texas, Austin, and the Portland State University and our partners. So we are very honored and very excited to be involved in this project. For this project, what we will do is that we will change a portion of this grid following wind turbines, double-fed induction generators to grid forming, update a portion of wind turbines to grid forming, and also we'll install a grid forming battery in this side eventually. So this side will be a hybrid grid forming and a grid following plants, and also with solar wind energy storage. This seems to be a very exciting and also challenging project. But if successful, this will be the nation's first bulk power system connected grid forming hybrid plant. So very meaningful project to industry, in my opinion. And I already visited this site 3 times because it's just a 1 hour and 15 minutes drive from my location. And this project will be closely coordinated with the UNIFI consortium. For example, the REGFM B1 model, which was mainly supported by GE, will be used for this project for some initial simulation studies. And also, once we have more field test results, those will be used to further identify the limitation, and potentially we need to update these REGFM B1 models to better reflect some features of grid forming inverters. I know no models are perfect, especially for the first one, right? So we know RGFM B1 has some good benefits and show some main characteristics, but this model can always be improved to better reflect what happened in the real world. Okay, so here I have a very quick, brief introduction of both RGFM A1 and the RGFM B1 models. So this feature This table summarizes the main feature of those two models. You can see for normal operation, REGFM A1 model represents droop control, and REGFM B1 model represents the virtual synchronous machine control. So we know that's mainly referred to their normal operation. But actually, when we develop those models, actually 95% efforts was spent on handling how they deal with abnormal operation mode. That means when their limits are reached for different kind of events. So you can see for REGFM A1 model, we have a steady state active and reactive power limiting control. We have a transient current limiting control, which is equivalent to a virtual impedance control. This is kind of well-published approach in the literature. But also we mentioned that there were no advanced fault rise-through control. So that means there is a critical clearing time there. You can do the typical faults, but doing long-term faults, it will have a critical clearing time. And for our GFM B1 model, it has a transient current limiting function, and also has a steady state active and reactive current limiting, and also has a Pico priority algorithm to determine the steady state ID and IQ. And also, again, GE provided a very good fault rise-through control in this model, so there is no critical clearing time based on our studies. So this table basically summarizes the main features of those two models. And then we have these models I mentioned. We want to collaborate with utility industry to help them better evaluate how these models could impact the grids. So just show some examples here. We worked with WECC. WECC published a report on grid forming technology using this model. Also, we worked with ERCOT, did some initial evaluation using this model. And also, we worked with Puerto Rico and to study how these grid forming inverters can impact the small islands. Actually, there are more results, but here I just show some example here. This is just show some simulation results from industry using these models. So you can see at the left side is actually the WECC. They published the report on the system frequency response with grid forming inverters. And then the previous case I showed was a micro WECC system, just a very small system. But this simulation results actually was conducted on a full WECC system. It has 20,000 buses, maybe thousands of inverters. And they find that, look at this green line and the blue line, if we have grid forming inverters and with some headroom, they can significantly improve the system frequency response compared to the traditional grid following inverters. That's the major benefits of grid forming inverters. And also WECC provides some recommendation to recommend this grid forming technology. And the right side is actually simulation results done by ERCOT using this REGFM A1 model in the WECC system. In the WECC system, because they want to, in their case, they have a very weak system, like to connect some renewables to the WECC system. And then they like to, they also have some battery storage there, but they find that if they have that battery storage as grid following, they will see some oscillations post-fault, which is just reasonable because we know the issues with grid following inverters in WECC system. But if they use battery as a grid forming, you can see those oscillations were gone. This just show the benefit that grid forming can have mitigating oscillations in the WECC system. So this just shows some benefits of the grid forming inverters that can bring to the system. No, we didn't say that we solve all the problems. There are still a lot of things we need to further understand, especially for grid forming inverter behavior under constraints. But I think we already see the clear benefits that grid forming inverters can bring to the system. And here are some conclusions. So for this presentation, we mainly introduced the major accomplishments conducted under the UNIFI consortium for developing those first WECC-approved standard library grid forming inverter models. These models now are available in all those commercial tools. So if you are using those commercial tools, you can easily find the models in your tools. And also here, I like to emphasize the importance for the collaboration between inverter manufacturers, software vendors, system planners, and research institutes on developing this kind of standard library models. I think that's very important. So this figure actually shows the life cycle of this model development. You can see that when we develop the initial model specification, we work with WECC to approve them. And then software vendors start to implement the model and benchmarking the model. And then finally, once the benchmarking is done, and then this model will be approved by WECC. And that's the status of REGFM A1 and B1. But this is, you can see this is just halfway, right? Next step, when we have more grid-forming inverters deployed in the field, the software vendors start to, the planners start to use this model and will provide feedback. They will use this model for their interconnection, the base case creation, or for some connection studies. And then once we have more grid-forming inverters deployed in the field, we'll do model validation against these models. No models are perfect, and we probably will identify some limitations of these models, and then we'll also work with manufacturers, software vendors to maybe improve these models and needed. And then we can work with the industry again, WECC again, to update these models. So this just shows the life cycle of this standard library model development. But we really believe this kind of collaboration between manufacturers, software vendors, system planners, and also some research institutions are very important for this model. So we made some initial progress, but we think there's still a lot of work needs to be done as we all better understand this grid-forming inverter technology together. And finally, I'd like to provide an immediate next step because we approved the REGFM A1 model and REGFM B1 model, which basically represent droop control and virtual synchronous machine control. We thought those two controls represent the mainstream grid-forming controls used in the industry. Although we know different manufacturers will probably have different fault rise-through control, those type of things. But then, based on our recent collaboration with Tesla, we realized that there actually is another representative grid-forming technology used in the industry, mainly by Tesla. So actually, this figure basically show the high-level concept. They implement both grid-forming and grid-following control inside one inverter. It's not just about switching between control modes. They're both controls actually working in parallel within one inverter. So that their single inverter behaved as a voltage phaser in parallel with the current phaser. So I think this is also very interesting idea. And also we can see that because of our previous work, more manufacturers are willing to join us on this effort. So Tesla, we're having very close collaboration with Tesla on developing the third model. And hopefully you will see more details of this model next year. And hopefully we can be released next year sometime so more people can see more details about this control. So yes, so that's the presentation from my side, and thank you for your attention, and I'm open to questions now.
Yeah, thank you so much, Wei. Very interesting work. Let me see.
Maybe
then
I
maybe I
can
stop the recording.
yes, let me stop.